Hello everyone, I bring my greetings from IIT Kanpur. We have been looking at unit processes in this course on IC fabrication and semiconductor processing basics. So far we have been looking at additive process where we add films and layers or material inside the substrate by implantation or whatever, or a whole range of them. Then last lecture we discussed about lithography, where we pattern the wafer and decide from where we need to remove the material. In this lecture, I would like to discuss about the process of removing material from a substrate. So this is about etch processes broadly, that's the topic. So let's get started. So this is a unit process on etch processing. The disclaimer, this will be the outline of today's talk. First we'll talk about wafer cleaning. In a way, that's also a subtractive process. You want to get rid of unwanted stuff that may be there on the wafer. Then we'll talk about etching in two forms. One is the wet etching, another is the dry etching. And then we'll talk about a method of subtractive process, which is a chemical mechanical polishing, which is very important in today's IC fabrication. I'll just like to highlight that. I won't be going into very much detail, but I'd like to highlight that. So let's get started with wafer cleaning. Wafer cleaning is a very critical step. We may not realize it, but when you start with a wafer, you want to make sure it is as it should be. Ideally, it should be pristine. If it went through some other process, we would want to make sure whatever was the residue or some contamination that might have come in the meantime, as it was waiting for the next process, those should be removed. So wafer cleaning removes contaminants that may affect the device yield and performance. And we have seen that it plays a very crucial role, and sometimes the whole process parameters change if it is not cleaned properly. Invariably, a critical part of VLSI processing is ensuring this will ensure that the device fabricated will work as it should. And one of the critical parts is to clean the wafer properly. It is needed to ensure the process is predictable, because contaminations are not in our control. So one day you'll have one contamination, some results, next day another contamination, another result. So you want it to be predictable, reproducible, and of course we want to have very high yield. It should not be that only a few devices work. We want preferably all the devices working. Now, what types of contaminations are there? What sources of contamination are there? Actually, it turns out there are a wide variety of contamination that is possible. And the whole idea is to keep out all of them, and that itself is a big challenge. So whenever we identify a source of contamination, we try to remove it at the source itself. It's not that after contamination we agree to clean it. It's like cleaning a room. If you want to clean a room, you want to make sure that you avoid the room from getting as much as possible from getting dirty. It's not that you put dirt and then clean. That won't help. And sometimes we may not be able to clean it perfectly, and so some dirt will remain. Same with wafers. So if you allow contaminants to come, we think we are cleaning it, but who knows, we may not be cleaning it perfectly. So it's a good idea to make sure we avoid contamination at the source, but there is a limit on how much we can do, but we try our best. Now, once, irrespective of what we have done to make sure contamination sources are not there, we try our best to make sure unknown things are removed. Unknown contamination that might have come will also get removed. So we have a standard cleaning procedures. So there are many established wafer cleaning procedures that are present, and each industry may have its own proprietary ideas, and also it depends on the type of technology one deals with. Wet processing could be carried out in baths that are built into benches, wet benches, and they are under laminar flow showers, so there's no particles or dust that are coming from outside. So you make sure that whatever is on the wafer gets removed, and after it's removed, it remains clean. Similarly, you'll have a drying process, and sometimes rinsing as well, and it is carried out in centrifugal systems. Now, particulate cleaning may sometimes involve ultrasonic scrubbers, as we will see, and sometimes some people have to resort to some extreme steps. Sometimes native oxides may form. and you may want to sputter clean it. People have tried that. Not all of them have been very successful, but those are some ideas people are looking at. So what are the sources of contamination? The sources of contamination, first, of course, both are equally important, but particulates is one of the common sources of contamination. Essentially, these are bits of material which are known boundaries. It's not a film or something. It's something that comes, floats in and falls on the wafer, or some part of some structure that was there breaks and comes. Some photoresist was there, forms a flake. So these could be silicon dust, quartz dust, or even atmospheric dust. Although we have clean rooms, but who knows? One has to be very careful. And there's always one dust particle that's enough to mess up a die, right? So we want to make sure we avoid it. And even if something had come inadvertently, we get rid of it. Then also, it can originate from clean room personnel, people who are working there, human beings. We emanate particles. We don't realize it. When we breathe, particles come out. So when you speak, particles come out. So there is protection that is given, but all the same, we need to make sure, and they do give clothing, but still you never know. Clean room clothing is worn and people have masks and so on, but all the same, there could be particulates coming from personnel. Clothing, street clothings that are inside the clean room gowns, if sometimes they may get exposed and they may cause lint and other stuff. And processing equipment as well. It may be that we have used a processing equipment and it does it very nicely, all the process, but the walls of the processing equipment is emanating particles which come and settle on the wafer. So before the next process, we have to get rid of it. Photoresist chunks, this is a very common source of particulate contamination, because at the edges of the wafer it forms beads, and while we try to remove it, and we'll be seeing how to remove photoresist remnants, but sometimes some things may remain and they may become particles which will come and cause problems. Sometimes even bacteria can be found. We use DI water, and as our dimensions are going to sub micrometer and nanometers, a bacteria which will grow in the water may end up being a contaminant. So we have to be extremely careful on this. This is about particulates, but there can also be films that are formed, and they remain, or they were not removed completely, and so on. So solvent residues. You may have used a solvent to dissolve and get rid of something, but the solvent itself contains some contaminants. Sometimes acetone, isopropyl alcohol, all this may be remaining. You never know. Some residue may be remaining, or residue that was present in the solvent may be remaining as a film. Photoresist developer residue could be there. Metallic films formed on wafers in baths, when previous wafers were cleaned, maybe some metals contaminations was there and they may get settled and form a film. And etchant or resist stripper baths, those are sources of those metallic contamination and other film contamination. We may have contamination, but we should be able to track them. And there are some standard procedures that are there. In fact, there is automatic defect detection system that is always often used in fabs. So you have this wafer and you shine light on this, and you collect the light and through an optical system, and then you integrate it and you photomultiply it so that you can accentuate any difference that is happening at some location in the wafer. And then finally a map of the wafer can be generated, and this gives an image of places where there is something out of place. Of course, these are easy when the wafer is pristine and you're starting off with a plain wafer. When there are patterns, it becomes more tricky, but this at least highlights what is out of the way, and then you can analyze this and then go back and see what's the source and get rid of the source of contamination, and also make sure the wafers are cleaned appropriately. So let's first talk about chemical removal of film contaminants, and this is a standard which is likely to be helpful for even when you do experiments in a lab, in a college lab or a university lab, where you're wanting to do some simple processing. So let's see what are the type of chemicals we can use to get rid of certain types of contaminants. So mainly one of the popular source of information about cleaning of wafers is RCA cleaning. This was developed in RCA, Radio Corporation of America, by Kern and Puotinen. So they have developed a process which has sort of become a standard. There will be tweaking here and there over time, And also in certain companies and certain fabs, they will have their own modifications and sometimes completely different ways of cleaning, but this is one of the most popular methods of cleaning a wafer. First is a preliminary clean. Okay, this, although you may have cleaned it earlier, when you start off, the idea is to start from scratch, assume the worst and be prepared for the worst and hope for the best by going through the cleaning process. So preliminary cleaning, actually this uses H2SO4, H2O2, real potent mixture. Okay, usually it is dehydrated H2SO4, H2O2, and this is, you give a quick clean on that and followed by DI water. Now what is DI water? DI water is deionized water. So you get rid of all the ions that are there in the water. So that way the water will be extremely good solvent. Anything that comes, it will dissolve very well because there are no ions present in it, and also it will not contaminate anything because there are no ions present to settle down and react with anything. Now how do you know how good the DI water is? Usually you check the resistivity of the water. So if it is 18 mega ohm per 18 mega ohm centimeter is usually the unit for resistivity and the resistivity value, which is usually considered to be a good quality DI water. So anything above 10 to 18 may be okay. Of course, you have to try your best to keep it as close to 18 or at 18. And usually it is done close to room temperature, 18 to 23 degrees. You do the DI water rinse and get rid of that H2SO4, H2O2 that was there, that you used for first step of cleaning. After this thing, we come to the organic cleaning. We try to get rid of all organic contaminants and certain metals. Now here you use a slightly basic solution, and again an oxidizing agent, H2O2 along with ammonium hydroxide, and it's a mixture with water. And when we say water, we mean DI water, which is extremely pure and very high resistivity when you started using it for the mixture. And this is at 75 to 80 degrees. You keep the wafers in that bath which contains this for 10 to 15 minutes, and then once it is done, you pick it up and you follow with a 1 minute rinse in DI water. So that way anything that any solution or that is present sticking to the solvent that is sticking to the wafer, or a solution of contaminants in the solvent that is sticking to the wafer, will also get cleaned up when you rinse it in DI water. After that, once you have a base, of course, next you should go to an acid, right? Here you use, there are a couple of steps you take. One of the steps you initially take is use HF and hydrofluoric acid and water. Okay, 1:10. It's a dilute HF dip, and this is for 15 seconds, a quick dip. Why is this? Usually this is used whenever there is a native oxide that may have formed, and you want to get rid of that native oxide, and for that you do that, and then transfer it to a rinser 20 to 30 seconds, and then quickly, without drying, you take it to the next step. Of course, in case there was already some oxide that was growing, there was a layer which contains oxide, then this step could be skipped also, because I don't think one would imagine it will not help much, right? Because you already have an oxide, you are just removing a small thin layer of the oxide on the top, so it may not be that useful. So but this is a call one has to take. Sometimes removing a thin layer of oxide on the top may also be considered good, because it will remove any contaminant that is there along with that oxide that is going away. Then following that, we come to the next main key, main cleaning, desorption of remaining atomic and ionic contaminants. For this, we again use another acidic mix, H2O, HCl, and the oxidizing H2O2. Okay, in this ratio at 75 to 80 degrees again, and this is again for another 10 to 15 minutes. And once this is done, you again go through a DI water rinse. So once so first organic cleaning and then acid base cleaning to get rid of all the contaminants and metals and so on, and then following that you do the drying. In this, DI water is poured on that things, and very often you may have these type of dryers that are available, where first it's like a washing machine sort of thing, where you have this wafer cassette which is loaded into that, and then water can be sprayed onto it, and then it will rinse it for some time, and then it will spin it. Or you could even rinse it in a bath and then put it into this faucet dryer, depending on what the setup one has. But once this is done, you take it for the actual processing. You don't wait. You try your best that as soon as the cleaning is done, you immediately take it to processing, so as to avoid any other contaminant from making its way to the wafer before the next process step. So usually it is done by dump transfer. By dump transfer, we mean we have a cassette, we put another empty cassette on top and then just invert it. So all the wafers in one go will end up transferring into the other one. It's not like one by one you move the wafer. Those things are to be avoided, because first of all, it exposes it to more sources of contaminants, including the person who is handling it. Or even if you are using a machine, it is having to handle it. So you have to do it as fast as you can, and then you go for the high temperature process. Then usually after cleaning, you don't store it. You try to make sure the process keeps going, but sometimes you may have to wait because the equipment might not be free. In that case, you send it to storage, and you have to be careful how you store it. You put it in a glass box, glass container, and then you have a nitrogen dry box. So there is no humidity, and nitrogen is flowing, pure nitrogen is flowing, and you ensure that there is no reaction. As far as possible, oxygen and other things should be avoided. So this is the standard process that's often used in the industry and in many labs as well. We saw the generic cleaning, but one of the places where cleaning keeps coming again and again is in getting rid of photoresist. Many times after the lithography step, you'll have to remove the photoresist completely, and sometimes if there is some error also in between, you might have to remove the photoresist. So such things can happen. So photoresist removal is a very important step. So let us see what are the standard methods that people adopt. One is you can use organic strippers for removing the photoresist. Usually these are phenol based strippers, and they do work, but they have limited shelf life, or as they call it, the pot life. Once you keep it in a pot, and how long, because its effectiveness may decrease if you don't prepare it fresh and get it. So that's one reason that sometimes you may want to avoid it. And also phenol disposal is an issue. Remember that we don't want to contaminate the environment in the process of doing our semiconductor processing. So we have to be careful how we dispose all these after it removes the photoresist. So it becomes a problem. And also these sometimes can attack metal patterns that may be there. So you want to avoid it. So hence there is a move towards low phenol and phenol free organic strippers, which are also available nowadays. So the move is towards that. The other thing which is more common, at least I have used this in some places, is oxidizing type strippers. This is similar to the first step that we talked about earlier in the wafer cleaning. This is H2SO4 with an oxidant, and often the oxidant is H2O2. This combination, which is kept at very high temperature, 125 degrees, is given a very formidable name. It's called piranha. Piranha, as you might remember, is the fish found in Amazon River, which is known to strip any animal or something that is coming into the water to the bones in a few minutes. So all these fish will come and just eat up, right? So this is a very colorful name for a cleaning agent, but essentially what it does is it's supposed to be that effective in getting rid of stuff. Okay, so but then when you use H2O2, the byproduct is H2O. When it oxidizes, it gives one of the oxygen atom and becomes H2O. That means with time the solution becomes more and more dilute. So that means you have to keep replenishing more often. So that is it can be done, but it's an additional pain. So what people are moving towards is ammonium persulfate, where you don't have water as a byproduct, and so the oxidant, when it's used that way, it increases the bath life. Okay, you have to change the solution not so often as you might have to do if you had used H2O2. So this method allows for residual free removal of post bake and other difficult to remove resist. In fact, sometimes photoresist can be very stubborn, especially when you have done the post bake. After the lithography and before the process, you do a post bake, and sometimes during the processing also it may become more hardened. Sometimes you purposely harden it by implanting into the photoresist, so that it doesn't give way during the main etching process or something. So given all that, um, uh, removing these can be a challenge, and these will can work, but of course, as you can see, you're dealing really potent solutions. One of the things that has become increasingly more popular today is to use dry etching for the resist. You just burn it off, ash it, and at the end you do again another clean. Of course, again one wet etch will be there, but at least the main part of removing it, you just burn it off, because photoresist, remember, is just an organic material. So you just end up getting carbon dioxide and water in the end. So so you can actually use oxygen plasma, which ends up being very effective in reacting with this and gets rid of it. And usually it is safer to handle, and there is no metal contamination because there is no solution in which you are the bath in which you are dipping it, right? So there is no previous material that would have some metals dispersed in it, and that somehow is lurking around and it shows up when you are trying to do the cleaning. So it's safer to handle, no metal contamination, less, comparatively less pollution, and underlying structure is better preserved in this, because sometimes during these piranha etch and other potent etches, the other structures may get affected adversely. So that way it is better preserved. Following the etch, of course, you have to do a quick clean in this. You give a short dip in that dilute HF solution, day water rinse, and then 20 minutes 80 degrees centigrade in the H2O2 ammonium hydroxide solution. If you will remember, this is the last a couple of steps in the cleaning part of the RCA cleaning before the dryer thing. This is what was done. Then following that, of course, you dry it up and remove. This step is to remove any monolayer that is lurking around. It is true you have used oxygen plasma to etch it and all that, but sometimes the photoresist might have seeped to the backside of the wafer and so on, and you may not know, and you don't want all this, so you have to get rid of anything that is there. So it's just to be doubly safe, you do this wet etch after the dry etch as well. But that being said, dry etch is the more popular etch today. Special care is needed to remove photoresist from the wafer edge, as I said, and that actually is a challenge, and people have techniques developed to make sure that specifically the edge of the wafer sees the solution, so that solvents, so that they get removed, the photoresist get removed. And part of the reason is you have bead formation. When you spin coat, it goes to the edge and it forms a slightly hillock type region all around the edge. So that's what is known as the bead. So that can end up causing particulates. So you have to take special care for that. How do you remove particles? Now, this over time, a lot of interesting ideas have developed, and some of them have come for many decades actually. One of the things that is very popular, and you may even find it in your labs, I don't know, if you are doing processing, you might have used it, is to use an ultrasonicator. So ultrasonic scrubbing, as it is called, at a very high frequency, sonic waves are sent into the solvent in which the wafer and other things are dipped. And so because of this vibration, bubbles are formed and they are again collapsed. As they collapse, they send out waves out, and that ends up stirring all these particles and removes them from adhering to the surface and brings it to the solvent, and the solvent is replenished, so that way you get rid of it. Today you have even higher frequency 850 kilohertz and megasonic cleaning systems. This is an image or the cartoon of a megasonic wafer cleaning system. So you have these wafers sitting there, and then you create these waves, and they go past this, and you can see the particles will be removed from the surface, right? The sonic energy will go this way, and so the particles will be removed and they will be away from the removed from the wafer. Another hands-on, if I may say so, approach is high pressure spraying and brush scrubbing, good old scrubbing. But of course, these are sophisticated equipments. You have a cup type brush here in a brush cleaning station, and the wafer is here, and then it goes around the wafer. It doesn't exactly touch it, but with some liquids and nitrogen and other things, it ends up unsettling all the particles and removing it from the wafer. So this is one of the ways in which you can do this. This is particularly important after you have done some sawing or and so on, so that silicon particles and other things that may have stuck, you want to make it come out loose. So what are the takeaways of wafer cleaning? Many sources of film and particle contamination exist. We want to avoid contamination at the source itself as much as possible. Chemical processes used to clean the wafers between every step. Every unit step, invariably, there is a cleaning step. And because you don't want to bring contamination from the previous equipment to the next one and so on. RCA process is one of the standard processes that is available, and proprietary processes would be developed, and maybe you in your lab also may have your own specific process, because you know what is your main source of contamination, and you may want to emphasize on that and make sure you get rid of it. Photoresist stripping has to be done very properly, and among all the things, this is where, because you are coating something on the substrate and you have to remove it, and you have to make sure that what is to be removed is completely removed. And oxidizing time strippers are usually effective, but dry etching is more convenient and is used nowadays more. Particulates can be removed by sonicators or brush cleaning systems. So this is a nutshell about how cleaning is done, and this is something you may want to learn, especially if you are doing semiconductor processing. Proper cleaning of wafer is imperative for good yield, and this is all the more reason you have to learn this. So now let's look at wet etching proper. So far we talked about contaminants being removed, but now maybe earlier structures that were put there for some reason have to be removed. So let's look at wet etching. I'm broadly borrowing material from Wolf and Tauber. There are also good discussions in Saurabh Gandhi's book and SMZ's books. So this is the outline of what I would like to talk. First, I will talk about some, at least I would like to mention about some key parameters that often comes up when you're talking of etching. Okay, and note that I'm talking about wet etching, but the same ideas are also valid for dry etching, because those are parameters or terms or properties that you look forward in etchants and in etching processes. Then I would like to talk about as a case study or general examples, because as somebody who is wanting to know about semiconductor processing, there are some standard etches you should be familiar with, and at least these 4 I would like to just mention, and you can take a look, and they may be helpful for you in other lab exercises, etc. So what are the key parameters that we need to watch out for during etching? First, they talk of a bias. What they mean by bias is, following the etch, if supposing there is a pattern and there is a masking layer and you are etching through the gaps in the masking layer, so how much of the etching is happening more than what the masking layer is allowing? For example, there's a mask here and then you are doing the etching, so ideally this portion should go away, but in reality this portion goes away, but also something goes underneath. How much it goes underneath is called the bias. And notice this bias keeps increasing as you increase the time for which the etching is done. Okay, and usually this is more in the case of what we will see is isotropic etch. We'll talk about that. Tolerance is process to process variation. If I do one process and next process, how much is the etching rate and how much is the bias that is happening, that variation is important. There's something called etch rate. This is something very critical, as you would imagine. It tells you how long you need to do the etch, and this is the rate of removal of material. Then there is anisotropy and isotropy of etch. Okay, anisotropy means directional etch. Isotropic means etching same in the all in the same direction. Now we have come across this example of anisotropy. Sometimes you want it to be anisotropic. For example, when you made these spacers during the process integration, we discussed about the gate poly, and on the sides we made spacers. We were able to make them only because we were using anisotropic etch. So it etches only directionally and equal amount in all places. So wherever in the corners where more amount was there, they won't get etched. So you will find that this regions, the 2 edges, they remain. And this is what is anisotropy, and in all etch process we want to know what is the anisotropy. Is it directional, or does it etch in all directions? Then there are some standard things that which you might also be aware of. Selectivity. Supposing I'm etching silicon and there is silicon dioxide. I don't want the silicon dioxide to be etched as far as possible. So I would like to have selectivity in etching the silicon, or vice versa. If I'm etching the silicon dioxide, don't want the silicon to etch. So there should be selectivity in etching the silicon dioxide as compared to silicon. So you want the rate of etching in silicon to be as low as possible compared to etching in oxide when you are etching an oxide. Okay. So difference in etch rate of two material. Over etch. This is something that has to be done very often, because you know that you have to etch for say 10 seconds to get rid of a film of a thickness say 10 nanometers. But then how do you know that the film is exactly 10 nanometers? It might have been 10.2 nanometers, or it might be 10.5 nanometers. So often what people do is the tolerance to ensure that the tolerance is respected, you over etch, you etch more than what you are supposed to etch. But in the process of over etching, sometimes you may end up eating more inside, right? As you can see, because of the over etch. So here it was under 0% over etch that was done. When 10% over etch was done, you can see the bias is increasing. And when 30% over etch was done, it's even more. So over etch is inevitable. It's a practical reality of because of the variations of the film thicknesses and etch rates that you may have. You just want to be safe, right? You want to do much more than what is needed and not just do just enough, because you never know. So you don't want to fall short. But in the process, there may be side effects. Then the feature size control. Invariably, etching nowadays is becoming for very, very small dimensions in VLSI. So small openings, when you do the etching, are the byproducts able to come out and get removed? If they don't get removed, the etch rates will become very slow in small regions. So the feature size that you can allow will be limited. You might have to make it larger to make sure the etch happens properly. So this is something that is controlled by the etching process itself. Then there is something called loading effect. This is especially true when you are talking about VLSI processing. You may have a full wafer, and if the density of etch in one region is different from another region, the loading effect is different in the two regions. So the rate at which the etching will happen may be different. Or in one wafer, the loading was amount of etching to be done was something, in another wafer it was different. It may affect. So you'll have to account for this. And sometimes even in the same wafer, if the wafer size is made bigger, only in the center it etches. Okay, if I'm not wrong, something called the bullseye effect or something, because it looks like a bullseye center. So you have to watch out for this. The loading effect is something that we often don't worry about when we are talking in theory. But in practice, when you are making a VLSI with many structures, every part of the die and every part of the wafer should have equal etch. So you want to make sure the loadings are similar. So sometimes you artificially create a load whenever you want to make sure it's even load all over. Or sometimes you may want to reduce the load also. You may prevent the density of etching to be restricted. So now let's look into some of the popular etches that are there. I want to leave you with some key things which I feel are important for somebody who's interested in semiconductor processing. First is silicon etch. Silicon etch, it can be both anisotropic as well as isotropic. So let's look at first isotropic etch. One of the most popular methods of etching silicon would be to use silicon to be etched by nitric acid and HF mixture, and usually you have acetic acid also added to that. Okay, so this is a very interesting, and then you can increase the temperature, and according to the temperature the etch rates will change, and also the ratio of HNO3 HF etch rate changes. That is sort of indicated by this iso etch curves given in this diagram on the right, which talks about the HF weight, HNO3 weight, and also the diluent weight. Diluent weight is acetic acid in this case. Now, what is interesting is, how does this take place? HNO3, as soon as it sees silicon and that to high temperature, it oxidizes it. So a layer of silicon dioxide is formed. HF loves oxide. So as soon as it sees it, it goes and gobbles it up. Okay, so HF and SiO2 have a very good relationship in terms of etching. Okay, so as soon as as soon as HNO3 forms oxide, he gobbles it up. Now again pristine silicon is exposed. Now HNO3 again goes and makes oxide. So one oxidizes, other eats up. One oxidizes, other eats up, and this is how the etching of silicon happens. That being said, if it is not controlled, and usually you try to have HF rate concentration be very low and HNO3 concentration be high. Otherwise, what can happen is it is such a rapid reaction. You may have pitting, and sometimes even porous silicon gets formed. In some combinations, you can get what is known as porous silicon, which has its own utility, and a lot of innovations have come out from that. So, but this is a very useful etch, and this is something you may want to know, as even if you are not working in VLSI directly, areas like MEMS and other areas where you have semiconductor processing, you may find this information about silicon etch useful, and you may be able to apply it, because there is a wide window of operation, right? Concentration of HF, HNO3, acetic acid, and the temperature. So all this plays, you can use as knobs for the way you get the etching done. It turns out wet etch usually is isotropic, because it's liquid will go in all direction the same way, right? But liquid may go in the same way in all direction, but the material that you have may not be isotropic. For example, crystals are not isotropic. So you may, as it starts etching, it hits certain planes where the etching rate is very low. So, and on the other hand, some planes of the crystal, lot more dangling bonds are there, it etches very fast. So you'll find that in the case of silicon as well, some etchants have the processes anisotropic. Okay, so anisotropic etch, what that you use KOH, potassium hydroxide. It's one of the most popular ways of doing that. So yeah, you mix it in with H2O in an isopropyl alcohol in these ratios, KOH isopropyl H2O in this ratio. It turns out 111 is the slowest etch plane. Why? It is the densest plane. So when it starts etching, there are a lot more atoms for it to remove. So the rate of etching is low. On the other hand, all the other directions, usually the etch rate is faster. So what do you find? You find that as it starts etching, the 111 planes get exposed. It turns out, and this is where you can sometimes make use of it, and as I said, in areas like MEMS and other places, you can make use of this structures for getting some diaphragm and so on. The slowest etch rate being that. So what you do is, if you use 100 wafer, the 111 planes will be like this. So you end up getting V grooves. In fact, this is same technique which could be used also for solar cells when you want pyramid like structures on the top. So you use this, but remember that it has to be 100 wafer. If it's a 110 wafer, you find that the 111 planes are all vertical. So you will have excellent etch, anisotropic etch like that. This is also anisotropic, but in this direction where 111 is in angle, and they call it V groove, and here you get it this way. So, and to give a comparison, for the etch rate that is there for various things, 100 plane will etch at 0.6 micrometer per minute. On the other hand, 111 is etching at 0.006 micrometer per minute. So 100 times slower. So clearly those planes will be exposed which are etching slowly. Okay, so this is a very interesting aspect of silicon when it comes to etching, both the isotropic etch that we saw as well as the anisotropic etch we saw. Now we come to some other popular etches, and you will do well to remember these, especially if you are going to do some processing or be involved with it. First is etching of silicon dioxide. Hydrofluoric acid loves silicon dioxide. Okay, and that's the etchant that is used for SiO2. So SiO2 plus HF will give hydrogen, silicon fluoride, and water. Okay, but then if you use concentrated HF, during the etching process, it may be so fast and it may end up affecting the photoresist and so on. So you don't want to do that. So very often you use buffered HF. And how do you buffer it? You put ammonium fluoride. That ensures that the fluoride concentration is remaining, doesn't suddenly dip or something, it remains constant, and there is a steady amount of etching that is happening. Another thing that you may often find, and which you already saw, is to use diluted HF. even 10 is to 1, 20 is to 1 also will be etching, and but it will etch the oxide. And as I said, HF loves oxide, but it hates silicon. As I mentioned here, HF will roll off pure silicon substrate. But if there is oxide, it will just spread out and try to stick to it and eat it away. Okay. So how do you know whether a wafer has silicon dioxide native film or not? You can put a drop of HF. If it spreads out, there is native film sitting there. If it rolls off because it is just silicon, then means there's likely there is no oxide. Okay. Of course, water also behaves that way. You don't need HF. Even water is hydrophobic to silicon, hydrophilic to silicon dioxide. Okay. But this etch is a very useful idea, and you might want to remember how etching happens. Silicon nitride, another material which we often encountered, it also has a wet etch, and the primary wet etch is orthophosphoric acid, 85% orthophosphoric acid, which is boiling at 180 degrees centigrade. Okay. Now this can be used, and it has good selectivity with respect to SiO2 also. So silicon nitride and silicon oxide, it does etch silicon dioxide, but not as fast. Okay. And comparatively, it etches oxide much more slowly. Okay. Nitride, it etches at 10 nanometer per minute. Especially LPCVD, it will etch much slowly, because LPCVD oxide is of very high quality. But photoresist will lift off, and especially you need reflex boiling. So it's not a very smooth environment. Very delicate features may get affected by that. So slowly the move is towards dry etching of nitride. People don't use wet etching as much, but you should remember that there is a wet etchant available, which is orthophosphoric acid boiling at 180 degrees centigrade, and that has reasonably good selectivity with oxide as well. That is, it doesn't etch oxide, it etches nitride. Aluminum etchant. The primary etchant is heated solution at 35 to 40 degrees of phosphoric acid, nitric acid, and acetic acid, and water. Okay. So these four constituents. The nitric acid oxidizes the aluminum, forms Al2O3, and then that is dissolved in phosphoric acid and water. This is very similar to the nitric acid HF game that was being played with oxide, right? Here it's actually with aluminum. Nitric acid will form Al2O3, it oxidizes, and that will be eaten up by phosphoric acid, and it will also dissolve in water. One problem you may face with this, they are traditionally faced also, is that bubbles of hydrogen may end up sticking to the aluminum. So those regions, the etching may not happen that well. So you will need to sometimes over etch it to make sure that it's completely etched properly. So those are some issues you may want to watch out. Otherwise, there may be bridging effect, because some bubble may be sitting that was not etched, and two lines may be touching. So you may have to over etch it. Over etch it means you have to spend a longer time doing the etching. So this, I have tabulated the various etchants. You are welcome to take a look at this. But these are very, it's not about memorizing, but getting a feel for what is happening, what is oxidizing, what is dissolving, and so on. So silicon can be etched by the HNO3 HF mixture. It can also be etched by KOH, isopropyl alcohol, DI water mixture. SiO2 HF, usually there will be buffered HF or the dilute HF. Silicon nitride for orthophosphoric acid, aluminum, orthophosphoric acid, nitric acid, acetic acid, and water. Okay. So this is just a table that sort of summarizes what we discussed, and some more details. So what are the takeaways about wet etching? Various parameters defined help track control of the etching process, and those have to be met. And what I have given is not just for wet etch, it's also true for dry etching. Silicon wet etch can be isotropic as well as anisotropic, and this is worth remembering, and depending on what approach you take. If you take the HNO3 HF approach, it is isotropic. It will etch in all directions, and you have to make sure it's not a rapid thing, so that randomly it makes the surface rough. You can use different constituents so that it smoothly removes the silicon. KOH, on the other hand, is anisotropic, and it will be limited by the 111 plane, and depending on the wafer you are choosing, you will find that that will be the plane that will be exposed. HF, especially buffered HF and dilute HF, is used for oxide etching and has high selectivity between silicon and silicon dioxide. Orthophosphoric acid is used for nitride etching, and that has good selectivity between SiO2 and Si3N4. So essentially, LPCVD oxide is actually even more resistant. PCVD may be a little bit more, may etch a little bit more fast. And the combination of these acids, phosphoric, nitric, and acetic acids with water, is what is used as an etchant for aluminium. Okay, now let's move to the topic of dry etching. Okay, dry etching is essentially where you don't have any wet bath or something where the etchant takes place. Of course, after the etching, you may have to do some cleaning, that's always there. So this is the outline of dry etching. I like to give the broad concept of what dry etching is, the key aspects with which people play, and some parameters and the physical quantities. Then I'll talk a little bit of plasma etching, and then conclude with discussions on reactive ion etching and ion assist, or sometimes it's also called ion assisted etching. Reactive ion etching is a very common term nowadays, RIE, and ion assisted etching is also another term that is used. So dry etching, let's look at it in this perspective. Let's look at the variation in pressure at which you are going to do the etching. Now, as the pressure increases, the excitation energy will decrease, or the other way, as the pressure decreases, excitation energy of the etching process increases. Physical sputtering is a very low pressure operation. Why? You are accelerating the particles that are supposed to sputter, and you don't want them to collide. So you operate it at low pressures. Usually you operate it as less than 100 millitorr, and they are usually highly excited. And what are the features that you are likely to find? This is actually brute force method. Physical momentum is just transferred. You accelerated a particle, it comes and just yanks away the atoms that are present in the film. It's directional because it doesn't care what is there. Whichever material is there, it will take, and also it will be very directional. Selectivity is poor, and it will only go in the direction in which the momentum is available. And there is potential damage due to this etch because it's brute force method, right? The other end of the spectrum of etching would be operated higher pressures. Here you do some little bit of chemistry, in fact lot of chemistry. You use plasma etching. You excite the electrons to such a high value so that and if the constituents of the gases that are present, they can come and slowly eat away the thing. At a lower temperature, what would have originally occurred, reaction would have occurred at high temperature because the electrons are excited. But the overall ion excitation energies are much low, so the damage actually is likely to be less. So this is more of a chemical process, faster because it's chemical, and if you have the chemistry right, it happens very fast, 10,000 times faster. It's also isotropic because chemistry in all directions, unless the material itself has some anisotropy, in all directions it will start etching. It is very selective also because it's a chemical reaction. Unlike the physical thing which is just bulldozing its way, this actually is selective, discerning. But whatever it can react, it will react very fast and less damage. So what you notice is the first process is highly physics based, just physical brute force method. Another is a fine chemistry based, but then physical brute force method can ensure it is more anisotropic, whereas plasma etching will be isotropic. Can you play with them? Can you mix and match? And that's indeed what engineers do. They took the best of both worlds and they ended up creating what is known as reactive ion etching. Okay, so usually halocarbon gases are used. So here what you do is you use physical ions and also use the chemistry. So a combination of those, and you have levers. Sometimes you can have more of the physics and less of the physics, more of the chemistry, less of the chemistry, and so on. So you can make it directional, and you can have it more selectively. You can have more selectivity as well. So this is done as you would expect. It's somewhere in between, right? The golden mean in a sense. So it's 100 millitorr range, somewhere in between the two, and the excitation energy also somewhere in between. and as far as damages go, it's also somewhere in between. Okay, so this is now actually a very popular technique of etching, because you can decide to make it directional, and also it has less damage compared to the brute force method. It has some element of selectivity as well. So let's see how the plasma etch process occurs. This is similar to some of the deposition processes we say. Only thing here is, here we want to take things away from the surface. So you have a plasma out here and gases flowing out here. So you have generation of etchant species, the species that will come and react and take away material. They are in the plasma state, so they are in excited state. So they diffuse to the surface. Then they get absorbed at the surface. This is we are talking about these gas molecules which are excited, and they have been absorbed at the surface. They end up reacting with this, and once they react, they form something else, and that may not be easily absorbed. Once it is reacted, maybe it may want to be more free, so that will try to desorb, and once it is desorbed, it will go out, and you should make sure you are able to take it away. So one of the requirements of good etchants is that the products that are formed due to etching, they should be very volatile. They should want to desorb and go away. Many times we find that the reaction takes place very well, but the products that form, they remain there. If they remain there, your etching is not going to happen, because next it will just form a film, and next thing will not be able to go and react. So that is one of the things that you have to play with. You have to make sure that whatever is formed is desorbed, is volatile, and it goes away. And you should ensure that all of these processes are facilitated. So this is how plasma etch takes place. Now, I'm quickly sharing some tables. You are welcome to look at it, ponder over it very carefully. Usually the gases you use for solid etching would be fluorine-based gases, and the byproduct of silicon dioxide, silicon nitride would be silicon fluoride. Okay, and you could also use chlorine-based, and and that you can usually use only when you are using silicon etching. Okay, that may not be effective with SiO2 and silicon nitride, because you have to make sure that the byproduct should be finely volatile, and you should be able to remove it and should react in that manner. Aluminium, you can again use a lot of chlorides. Many of the chloride gases and aluminum chloride, which is volatile, will go out. Organic material, we already saw that. We saw in the case of photoresist, we are using etching, right? Ashing. So you can use oxygen plasma, because what is byproduct will be carbon monoxide, carbon dioxide, or water vapor. And even if some other organic compounds, usually they are volatile and they'll go away. Sometimes you can use CF4 and oxygen together, and then you have HF also created. Refractory metals, this can be tricky. Again, here you have to make sure that the byproduct should be volatile. So carbon tetrafluoride can be used, especially with tungsten. You have tungsten for a hexafluoride that is volatile. So it depends on, you have to make the choice based on what the byproduct, it should react, and the byproduct should be volatile. Now, one of the things is interesting about this plasma processing is you can monitor what is happening. How? It is a plasma, so all the atoms are in can be at least a fraction, big fraction of them will be, significant fraction of them will be in excited state. So that means that you know what atoms are present, because there will be optical transitions of the electrons that are present. So by studying the optics, you can find out what is present in the chamber. So you can know whether the reaction has started. Have you etched if you have finished etching all the films, supposing you are etching, there is tungsten there, you have etched all the tungsten films, then you will no longer find signature of WF6, right? So that means you know that the etch is over. So that's the end point detection, they call it. So you over etch it a little bit, because you never know, maybe the sensor may not be too accurate. You over etch it and then you stop it. So endpoint detection is a very popular technique that you use to know whether the etching has happened or not. So for resist, these are the gases you will encounter, and these are the wavelengths. You can monitor them. As soon as the etching starts, you will find that the signals in these wavelengths will start coming. Similarly, silicon nitride, aluminum, you'll find that these are the signals that will come. So before you start, no signal. As soon as etching starts, signals start shooting up. As soon as etching is done, it will start going down and it will go towards zero. So then you know that etching is done, you can stop. So this way you can track and you can sense it. Now, from plasma assisted etching, I'll also talk a little bit of ion assisted etching. Ion assisted etching essentially is the chemistry alone won't work, the physics alone won't work. A combination of that will work. So let us see an example here. You can see here in the x-axis is the time, and right axis, y-axis is silicon etch rate. How do they know? How do they know silicon is etched? From those detections of the optical in the optical spectrum, depending on what gas is coming out. So xenon fluoride is initially put in. Some amount of etching is taking place. Then what you do, you also start bombarding the wafer with argon ions. Suddenly you find huge increase in the rate of etching. Then somebody comes and turns off the xenon fluoride supply. Argon is still bombarding. See, it has dropped down. So what this is tells is, what this is, it's very clear, and this is one of the early works that showed that this is possible. Xenon fluoride and argon combination is what is working. So you need the physics of bombarding with ions, and you need the chemistry of these atoms coming and reacting and it going away. Any one of them stopped, the whole reaction, so it stops. So it's working in combination. So that's what is exciting about this particular thing. So how do these ions help? Maybe a couple of theories and instances depending on what it is. So supposing you have this material, the ion actually is coming and bombarding and creating damage on the surface. This region it is not, right, because it's blocked. So when it is causing damage, more dangling bonds are there. And now if the gas come, it reacts much more easily. If the gas had come before the ion had the ion bombardment had taken place, or then it will not react, because the atoms are all well secure in their places. But the bombardment with the argon ion ended up making them exposed, then they end up reacting and going away. Another thing that often is end up using is, you can have surface inhibitors formed. So as a result of the reaction, whatever is formed is not easily volatile, okay, and they are absorbing quite well. But this argon coming and bombarding, whatever inhibitors that are there, they are ending up removing them, and then they go into the exhaust. So this is one of the tricks that you can use. And here you can see on the wall the inhibitors are present, so no reaction takes place on this side. So it can be very anisotropic, very directional etch you can get in this. So without having to use that brute force bombardment of physical etching, you can get the anisotropy by using ion assisted etching, using chemistry as well. So the ion cross bombardment helps the chemical reaction to go forward. So now let's look at a couple of instances, varying bias during etching. So here you have the etch rate indicated, and you have bias in voltage. This graph is shown for SiO2. What do you find? At 0 bias, etch rate is 0. At 150 volts or something, you have a much higher etch rate. Similarly for silicon, 0 bias, it's not zero etching, there is a small etching that is taking place, and very high bias, forward bias, rather reverse bias, you find that etch rate is high. Now this can be seen in the type of shape that you will get in the thing. So here left side you are seeing the etching that is taking place for silicon. Remember that the bias that is applied is in the vertical direction, right? In the horizontal direction there is no bias. So the etch that will take place in the horizontal direction corresponds to 0 bias. So this Vx is the rate of etch in the horizontal direction. Vz on the other hand depends on the bias that you are applying. So by changing the bias, you can actually change the shape of your thing. You can, in fact, there are examples of bottled trench and so on. People have attempted at various places. So of course that's more sophisticated. You may need certain other tricks as well. But simply by changing the bias, you can affect the rate at which vertical direction etch takes place and horizontal direction takes place. SiO2 on the other hand, there is no horizontal etch. Why? Because horizontally there is no bias, and there is only no etch in the horizontal direction, only vertical direction will take place, and that too depends on the bias. If you don't apply bias in the vertical direction, no etch will take place. So you can control how you are etching the SiO2. Very useful, especially for back end of the line processing and all that. So bias can be an option. It can be a lever to choose the extent of isotropy or anisotropy in the etching. Of course, it's material dependent, ion dependent and all, but it is possible. Let's also see, we saw that you can change the bias to tune it. Can you also change the chemistry to tune it? Actually, it turns out you can. Supposing you have the etching that is taking place at bias 150 degree, minus 150 volt. Okay, so what you find is, and x-axis is the percentage of H2 in the CF4 H2 mix. You can see that as H2 percentage increases beyond 30%, it will not etch, it will start depositing. Okay, it will stop the etch. And similarly, in the x direction, this is what you get. X direction, remember, there is no bias. X is equal to 0 bias. So you get this case where pure CF4 gas is there. Pure CF4 gas means H2 is 0. That means you have this much of VXH and you have this much of VZH. And the ratio of the H rates would give you the ratio of the anisotropy. And on the other hand, if you have 10% hydrogen in CF4, you find that horizontal H should be 0. You only have vertical H. So you see, it's a perfectly anisotropic H. Here, you can have an element of isotropy by increasing the x direction H to some extent. And you can tune it, make sure you inhibit the z direction. So you can make it equal on two sides. So left can be made isotropic, it will be more isotropic. This is clearly is anisotropic and directional. So gas mixture composition is an option to choose extent of isotropy and anisotropy. So you can use both physics as well as chemistry to get this. So let's take the takeaway of dry etching. One way to use physics or chemistry, one way is to use both physics and chemistry to carry out the etching process. We have not talked so much about the physics process, which is similar to sputtering. I have not discussed it much. But here, mainly if etching is done by chemistry, PECVD, or by RIE. So one of the use of both gives actually more leverage, and actually you can end up control better. Plasma etch occurs with the need for lower activation energy. Various etching recipes are developed for etching different layers in VLSI process. And the etch process is kept tracked by studying the radiation that comes out, because they are all in excited state and the light that is emitted is dependent on the electron transition. Ion assisted etch allows for more control in making etch isotropic or anisotropic, and both electrical bias and gas compositions, both the chemistry as well as the physics, can be used to control the anisotropy. Now let's quickly take a look at chemical mechanical polishing. This is a fascinating field that was actually invented in the 1980s at IBM, and by 1990s it had really come into play in almost all the VLSI fabs. It is an important method to remove material, but what is most important is when you remove, you leave a very smooth surface and a flat surface. Very important, as we saw in lithography, because depth of focus becomes an issue when you go for smaller and smaller wavelength. So you need flat surfaces. And CMP in a way helped a lot in that. And it's also helped in incorporation of copper electrodes, etc. So this is how chemical mechanical polishing works. You have a wafer which will be moving around. You have a polishing pad which will be rotating continuously. And there is a polishing slurry. This polishing slurry is the chemistry part of it. And the moving around is the physical part of it. Here too, as we just saw, you marry physics and chemistry and you get the best out of it. In fact, we use a chemical mechanical process in our daily life too. Good example would be brushing our teeth. If I brushed my teeth just with a brush without the toothpaste, it will get clean but not sufficiently clean. If I just use a toothpaste and put it on my teeth, it will clean my teeth but not much. But if I use a brush as well as a toothpaste, I get the physics of it, because scrubbing is taking place, the mechanical effort is taking place, and the chemistry also takes place, and together they end up cleaning my teeth, right? The same broad concept is used in smoothing the wafer. So chemical process, we use slurry. The slurry can contain abrasives, silica, ceria, cerium oxide, essentially alumina, aluminum oxide, silica is silicon dioxide, silicon oxide. Then you have also oxidizers, H2O2 and some others, pH conditioners, corrosion inhibitors. You don't want them to, because of the scrubbing, you don't want things to get hurt, right? Then you also have to, interestingly, you have to use biocides, again, because you want to keep bacteria away. Bacteria, I don't know, it finds its way to grow everywhere, I guess. So you want to keep it away. So you have to, the slurry will usually contain that. The slurry varies according to what one is polishing: oxides, metals, or STI. Ceria can be used for STI polishing, for example, and it chemically wears the surface down. It chemically, hence, making any rough edges, it just reacts and removes it. Mechanical part is, there is a pad here which grinds on the wafer as it rotates, is shown here. So the parts that are sticking out, they get rubbed more. And there is also all these abrasives that are there. They will facilitate in removing these peaked regions. And there is, of course, feedback control. Once you have physical process also, and it's moving, you can have feedback control to do more or less, release more slurry or less slurry, and overall you can control the process. And although it seems like a messy process, it can give certainly sub tens of micron and sub nanometer type smoothness. So really good smoothness one can achieve. CMP is critical for material removing process and ensuring global flatness in the wafer. That's important, because as the dimensions are becoming smaller and we are going to lithography with smaller wavelength, depth of focus is an issue. So you have to get this flatness. It has been the key for success of copper, because if you may remember, we discussed the Damascene process. Copper, there is no etchant, wet etch and dry etch. There is no successful wet etch or dry etch present. The only way they could do it was using CMP. So what you do is you deposit copper and then polish it off, and you stop at the place where you know that the other insulators are present, and from the signatures you know you have reached that. It also facilitates multi-layer interconnect possible. Because we are having such flat surfaces, we can reliably build multi-layered interconnect structures in the back of the wafer. Okay, so CMP is a very crucial element in VLSI technology. Let's summarize about etching. Cleaning of wafers is a necessary step, necessary evil if you want, you can say, because it's a must. If you don't do it, chances are your devices will not come out well. And in fact, the mark of successful device is often how well one cleans the wafer at the start. Traditionally, wet etching was the standard process. It helped actually the evolution of VLSI, and processes were built with very high cleanliness, what was needed for that time. And a variety of standards have also come up, which makes it easy for others to adopt and start making devices. But over time, dry etch has caught on. Dry etch uses both physics as well as chemistry, and usually the PECVD etching is popular, and also RIE etching is popular, and it has developed over time. And dry etch is often preferred over small dimension precision, and especially with the plasma, you have plasma sheets which can be very small, thin, so you can actually get into very narrow regions and all, and you can etch it very accurately. CMP process ensures one must keep the wafer surface flat after is able to keep the wafer surface flat after it is done, and today it is a mainstay of VLSI processing. You cannot do without it. Okay, so with that we conclude our current discussion on etch process. Hopefully it has kindled your interest and you will learn more about these and from various other sources.